There is a sheet of aluminum somewhere in your house that was smelted before you were born, and it still contains every joule of energy that went into making it. Aluminum does not self-discharge. It cannot, because until you add an electrolyte, it is not a battery at all, merely a metal sitting quietly under its own oxide skin, waiting. Add salt water, carbon and air, and it becomes a cell with a theoretical energy density of 8,100 watt-hours per kilogram, roughly 20 times what lithium delivers in practice. The whole build costs about $11. It runs once, and then you rebuild it, which sounds like a flaw until you consider what it replaces. A lithium battery that dies on a schedule whether you use it or not. In the drawer, waiting for an emergency it will not survive. Let us dive in. The torch in the drawer was dead when you reached for it. Not low, dead, with the battery still inside, having sat there for 4 years doing nothing whatsoever. Nobody used it, nobody drained it. It simply stopped working while being ignored. Lithium ages on 2 separate clocks, and most people only know about one of them. The first is cycle aging, and it behaves the way you would expect. Charge and discharge a cell repeatedly, and its capacity slowly falls. That is the number printed on the specification sheet, and it is the one everybody quotes. The second is calendar aging, and it runs whether you touch the battery or not. The chemistry inside a lithium cell keeps reacting slowly with itself, building up layers on the electrodes that were never meant to be there, and the process continues in a drawer, in a rucksack, in a cupboard, for years. 2 things accelerate it: heat and being stored at a high state of charge. Now look at how an emergency battery gets stored. You charge it to full because you want it ready. You put it somewhere warm and dry because damp seems like the enemy. And then you leave it completely alone for years, which is the entire point of an emergency supply. Every one of those decisions is the worst available choice for calendar aging. An emergency battery spends its whole existence in exactly the condition that kills lithium fastest. Then there is self-discharge on top of it. Slow, constant, and unstoppable, because the cell is a chemical system, and chemical systems do not hold still. So the device you bought specifically for the day the power fails is flat on the day the power fails. And the fix everybody settles for is a maintenance schedule. Check the batteries every spring. Rotate the stock. Replace them every few years, whether they were used or not. A subscription with a physical delivery, running quietly for the rest of your life. Which points at what emergency power actually has to do, and it is a stranger requirement than it first appears. It has to survive being ignored. An aluminum air cell does not go flat in storage, and the reason is that it has not started yet. 3 things are needed to make it work: aluminum, air, and an electrolyte to carry ions between them. Leave out that third one and no reaction is possible. The aluminum sits under its own thin oxide skin, chemically bored, doing precisely what an aluminum saucepan does on a shelf, which is to say, nothing at all. There is nothing to leak, because there is no liquid in it. Nothing to self-discharge, because no circuit exists inside the cell. No layers building up on electrodes, because the electrodes are not in contact with anything but air. Find a sheet of aluminum that was smelted in 1946 and left in a shed. Every joule that went into separating that metal from its oxide is still sitting in it, 80 years later, entirely undisturbed. Then you add water. At that moment the reaction begins, and from then on, it runs until the aluminum is gone. The switch on this battery is not a switch, it is a jug. Aluminum wants to become aluminum oxide, and it wants it badly. That eagerness is why the metal took so long to isolate in the first place, and it is also the reason this chemistry works at all. Expose fresh aluminum to open air and it grabs oxygen immediately, forming a thin, tough oxide skin across the surface. Then it stops. Not because the reaction has finished, but because it has been interrupted by its own product. The skin seals off the metal underneath and protects it. An aluminum air cell removes that interruption and collects the electrons on the way through. The structure is where it gets interesting. Most batteries carry 2 solid electrodes sealed inside a case, along with everything needed for the reaction. A metal air cell breaks that arrangement. One electrode is metal, The other is essentially an opening a porous carbon layer whose job is to let atmospheric oxygen reach the reaction while conducting electrons away from it. Half the reactants are outside the battery, and you never have to carry them. The reaction itself is straightforward enough to describe in one pass. At the aluminum face, atoms surrender electrons and dissolve into the electrolyte. Those electrons travel out through your wire, do whatever work you asked of them, and arrive at the carbon cathode. There, oxygen from the air combines with water from the electrolyte and takes them up. The two halves meet and precipitate as aluminum hydroxide, a white gel that settles out of solution. Now the numbers. Theoretical energy density for aluminum air runs to 8,100 watt-hours per kilogram. Practical lithium ion sits somewhere between 250 and 300. Real aluminum air cells fall well short of their theoretical ceiling, as every chemistry does, but even a modest fraction of that figure is a very large number. Voltage per cell is more modest, between 1.2 and 1.8 volts open circuit, depending on the electrolyte and the alloy, which is why these get stacked in series when anybody wants to run something real. Then the limit that defines everything about how you use one. The reaction runs in one direction only. You cannot push current backwards through this cell and turn aluminum hydroxide back into aluminum metal. That process exists, and it is called a smelter molten cryolite at nearly 1,000 degrees, drawing current measured in hundreds of thousands of amps. No arrangement of parts on a workbench is going to reproduce it. So this is a primary cell. It gets refueled rather than recharged, and the fuel is a fresh sheet of aluminum. The industry term is mechanical recharging, which is a courteous way of saying that you take the thing apart. There is a second limit, and it matters more for anybody actually building one. The moment electrolyte enters the cell, the aluminum begins reacting, whether or not anything is connected to it. A portion of the metal corrodes without delivering any useful current at all, and that parasitic reaction releases hydrogen gas continuously as it goes. The cell starts consuming itself as soon as it gets wet, and it vents while it does. On the 6th of December, 1884, workmen set a small pyramid of cast aluminum on top of the Washington Monument, because at that moment, nothing cheaper was considered good enough for it. The capstone weighed 100 ounces. It was the largest single piece of aluminum ever cast anywhere in the world, and the metalsmith charged $225 for it, well over his original estimate. Aluminum was going for $1.10 an ounce, twice the price of silver. Before it went up the monument, the pyramid was put on display in the window at Tiffany's in New York, and people queued along the pavement to look at it, the way you would queue to see a jewel. That was not an unusual attitude to the metal. Bars of aluminum had been exhibited alongside the French crown jewels at the Exposition Universelle in 1855. Napoleon III was said to keep an aluminum dinner service for his most honored guests, while everyone further down the table ate off gold. Now consider what makes that genuinely absurd. Aluminum is not rare. It makes up better than 8% of the Earth's crust, which puts it among the most abundant elements on the planet, more common than iron. There was aluminum in the ground under every one of those dinner guests. The problem was never scarcity. The problem was that aluminum holds on to oxygen with a grip nobody could economically break. That lasted 14 more months. On the 23rd of February, 1886, a 22-year-old named Charles Martin Hall, working in a woodshed behind his family home in Oberlin, Ohio, dissolved alumina in molten cryolite and ran an electric current through it for 2 hours. Small buttons of pure aluminum collected at the bottom. He had been experimenting with minerals in that shed since he was 12 years old. Across the Atlantic, a Frenchman named Paul Héroult, also 22, arrived at the same process within weeks and filed a French patent that April. The two men never collaborated and probably never met. What they had found is still the only method used to smelt aluminum industrially more than a century later. The price came apart almost immediately. $4.86 a pound in 1888, 78 cents by 1893, 25 cents a few years after that. Hall found backers and founded the Pittsburgh Reduction Company, which changed its name in 1907 to the Aluminum Company of America, Alcoa. He died worth $27 million. Within a single decade, aluminum went from a display case at Tiffany's to a material you could throw away. The capstone is still up there, incidentally. It has never been replaced, and it is never tarnished. Aluminum air cells are a real commercial product, and the customer list explains the technology better than any specification sheet does. The oldest market is military, and the reason is logistics rather than performance. An army needs power that can sit in a depot through years of storage, in heat and cold, unattended, and then work on the first attempt when somebody finally opens the crate. A chemistry that ages in storage fails that requirement, no matter how impressive its numbers look on a bench. The same logic covers everything else these get used for. Remote signaling, sensors in locations nobody visits twice, reserve power for equipment that must sit dormant and then perform once, correctly, without warning. Then there is the vehicle work, which is the application most people have heard about. Companies including Finergy have demonstrated aluminum air as a range extender, rather than as a main traction battery, and the distinction matters. The lithium pack does the daily driving and gets recharged every night. The aluminum sits untouched in the boot until the day somebody runs out of road, at which point it delivers a single large discharge and then gets swapped out at a service center. Nobody is proposing you charge it. That was never the offer. Laboratory work has been pushing at the boundaries as well. A group at the University of Hong Kong built cells on cotton and paper substrates, reaching around 900 milliamp hours per gram of aluminum, and other researchers have taken quasi-solid-state designs toward 4.56 kilowatt-hours per kilogram under test conditions. Look across all of it, and one requirement keeps repeating. Every application involves a long period of doing nothing, followed by one reliable discharge. So where does the energy in an aluminum air cell actually come from? Not from the air, not from the salt water either, which is doing nothing more than carrying ions from one side to the other. It came from a smelter, and somebody else paid for it a long time ago. Producing aluminum by the Hall-Héroult process consumes somewhere between 12.5 and 14,000 kilowatt-hours per ton. Divide that down and you get roughly 14 kilowatt-hours of electricity for every kilogram of metal. Consider what that electricity is buying. Aluminum in the ground is already bound to oxygen. Bauxite is, chemically speaking, aluminum that has finished reacting. The entire purpose of a smelter is to break that bond to force the oxygen off against the metal's own preference, using molten cryolite at nearly 1,000 degrees and current measured in hundreds of thousands of amps. The energy does not vanish into the process. It stays in the separation. Aluminum metal is aluminum held apart from the oxygen it wants, and it holds that position indefinitely as long as it stays dry. An aluminum air cell simply lets the oxygen back in, slowly, through a wire, and collects part of the difference on the way. Now the honest accounting, because the arithmetic is unflattering. 14 kilowatt-hours went in per kilogram. The theoretical maximum you could recover is 8.1, and a real cell delivers a fraction of that. Measured as an energy storage system, from smelter to socket, this is genuinely poor. A lithium battery returns most of what you put into it. This returns a slice of what somebody else put in, which turns out not to matter at all for the job it does. You did not pay for the charging. It happened years ago, in a plant deliberately built where electricity was cheapest beside a hydroelectric dam in Quebec, or geothermal generation in Iceland, or Norwegian hydro. And in all the time since, that charge has not leaked by a single joule. Nobody suppressed this technology. The reason it is not in your torch is commercial rather than sinister. Consumers were sold on rechargeability, and rightly so for most purposes. A cell you have to open, empty, scrape, and rebuild by hand loses that argument in a shop every single time, against a product you plug into the wall. So look at what that leaves sitting around you. Aluminum smelters are, functionally, the largest and longest-running battery charging plants ever constructed, and their output has been distributed into every kitchen on the continent. There are kilograms of charged cells in your house right now, in the foil drawer, in the recycling bin, in the ladder against the garage wall, and in the window frames. The build is 4 layers pressed together, and the order of them matters more than anything else in this video. If you want the full build, the electrode preparation, the cathode options, and the series wiring, we put together a complete walkthrough covering everything here and more. The link is in the description below. Start with the parts list. Heavy gauge aluminum sheet for the anode, activated carbon, a conductive mesh, cloth or paper towel for a separator, and salt. Around $11, and most of that is the carbon. Now the stack. From the inside out. Aluminum first. This is your fuel, and thickness buys you. Runtime foil works for a demonstration and disappears fast, while sheet gives you something that runs for hours. The separator sits against it, soaked in salt water. Its only job is keeping the two electrodes from touching while letting ions pass between them. Then the carbon layer, pressed against a conductive mesh that carries electrons out. This is the cathode, and it is the part that determines whether the cell performs or disappoints. And then air. Nothing else. The outer face of that carbon has to stay open to the atmosphere, because the oxygen arriving there is half of your chemistry. Roll or fold that stack so the carbon face stays exposed. Connect one lead to the aluminum and one to the mesh, and wet the separator. Expect somewhere between 0.7 and 1.2 volts from a saltwater build. Stack cells in series for anything useful. One preparation step matters enormously, and it is easy to skip. Scrape or sand the aluminum immediately before assembly. That protective oxide skin is what gives the metal its 80-year shelf life, and it is also an insulator standing directly between you and the reaction. The property that makes storage possible has to be removed to make power possible. Now, 5 rules. 1. Never seal the cell. Aluminum in electrolyte gives off hydrogen continuously, with or without a load connected. Hydrogen accumulating inside a sealed container near any spark is not a leak, it is an explosion. Open air. Always. No exceptions. No lid. 2. Build the saltwater version. Lye-based electrolytes deliver substantially better performance, and they will also blind you if a drop reaches an eye. That is not a reasonable trade on a kitchen table. 3. Activated means committed. If you want to pause the cell, drain the electrolyte and dry it out, because leaving it wet consumes your anode around the clock while delivering nothing. 4. Expect the gel. Aluminum hydroxide builds up on both electrodes as the cell runs, clogging the carbon and coating the aluminum until the reaction strangles. That is the chemistry working correctly, not a fault, and cleaning it is part of the job. 5. Ventilate and cite it somewhere you do not mind ruining. This is a wet, gassing, mildly alkaline system with a byproduct that sets like paste. It belongs on a bench in a garage, not on a kitchen worktop. 5 things that only matter once the first cell is sitting on the bench, dripping. The first is alloy, and it separates a good build from a frustrating one. Pure aluminum is a poor anode. It corrodes parasitically at a furious rate, meaning a large share of your metal dissolves without ever pushing an electron through your wire. Commercial cells use specific alloys with trace additions of elements like tin, gallium, or indium, chosen to disrupt that self-corrosion and keep the surface active. This is why a soda can and a purpose-made anode behave so differently on a bench. Beverage cans are also lined internally with a polymer coating, which is an insulator, and that has to come off before anything works at all. The second is that your bottleneck is the cathode, not the fuel. Almost everybody building one of these instinctively adds more aluminum, and it changes very little. Output is limited by how quickly oxygen can reach the reaction sites in the carbon layer. Widen that layer, make it thinner, make sure it is properly wetted on the inside face while staying open to air on the outside, and the current climbs. Double the aluminum, and you have doubled your runtime without touching your power. The third is temperature and concentration, which pull in 2 directions at once. Warmer electrolyte and a higher salt concentration both raise output. Both also accelerate self-consumption, because the parasitic corrosion speeds up alongside the useful reaction. Tuning for the highest reading on a meter gives you a cell that empties itself faster. Tune instead for the discharge rate you actually want. The fourth is the boost converter. At around a volt per cell, running anything modern means either a long series stack or a small low voltage boost circuit. The boost circuit is cheaper, smaller, and considerably more forgiving of cells that are not perfectly matched, which yours will not be. It also lets a stack keep working, as individual cells fade at different rates. The fifth closes a loop from earlier in this video. Aluminum hydroxide, the white gel clogging your electrodes, is not waste. It is precisely the feedstock the smelting industry already refines into alumina. Spent aluminum air anode material is ore, which means the same industry that charged your cell 80 years ago is set up to charge it again, and very few chemistries on Earth can say that. This runs once, and then you take it apart and rebuild it. There is no version of this that recharges. The aluminum is consumed into hydroxide, and returning it to metal requires a smelter rather than a charger. Once the electrolyte is in, the cell begins eating itself, whether you draw current or not, which gives a wet build a working life measured in hours or days rather than years. Output sits around a volt per cell, so anything genuinely useful means a series stack or a boost circuit, and it will make a mess of whatever surface you build it on. Every one of those is acceptable for the single job this chemistry does better than anything else on the market, which is to sit untouched for decades and then work on the day somebody finally asks it to. The energy in that cell was paid for a long time ago by a smelter beside a dam, and it has been waiting ever since without losing a joule. Two men aged 22 made that metal cheap enough to burn. In 1886, 14 months after the most expensive object on the Washington Monument was a lump of it the size of a fist. Every sheet of aluminum since has been a charged cell that nobody thought to use. If discovering the practical, unglamorous corners of engineering matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. We will be tracking all of it as it develops. Now go and find the oldest piece of aluminum in your house. A pan, a ladder, a window frame, a tent pole. Tell me what it is and how you know its age. I read every single comment.